Welcome to this Engineering Explainer. If you've ever stared at a completely overwhelming vehicle schematic, you've probably wondered, how in the world do dozens of distinct, absolutely critical car modules, like the engine control unit, the anti-lock brakes, the airbags, how do they communicate flawlessly without just crashing into each other's signals? It's a massive technical headache, right? But it's one that automotive engineers have solved brilliantly.
So, by the end of this explainer, you're going to have a crystal clear understanding of the physical and data link layers of CAN communication. We'll figure out exactly how to map a node's architecture, and you'll be able to accurately pin out standard diagnostic connectors. We're decoding the CAN bus together, so let's get into it.
Section 1. Inside a CAN node.
Let's dive right into the physical anatomy of a CAN network, starting with the individual nodes themselves. To never forget how this works, I want you to visualize a CAN node like a corporate office, okay? At the top, we have the microcontroller. The microcontroller is basically the boss. It runs the main application software, processes the real-world data, and ultimately decides what information actually needs to be sent out to the rest of the vehicle.
But like a lot of bosses, it doesn't actually speak the native language of the network directly, and that's exactly where our next component comes in, the CAN controller. Think of the CAN controller as the translator. It takes the boss's data and strictly formats it into the CAN protocol, right in the hardware. Finally, we have the CAN transceiver. You can think of the transceiver as the megaphone. It takes that formatted, translated message and physically converts it into the actual electrical voltage signals that travel down the vehicle's wires. So, just remember, boss, translator, megaphone.
Now, this brilliantly illustrates a CAN cluster. When you connect all of these distinct corporate offices together over a shared physical wire, they form a strict bus topology. And what's really fascinating here is that in a CAN network, every single node has totally equal rights to the bus. There's no giant central master node controlling everything. Any node can transmit data whenever the bus is free.
Moving on to Section 2, OSI model and standards.
So now that we have our corporate offices set up, we need some strict technical rules to govern how they actually interact. The absolutely crucial point here, especially when mapping CAN to the famous OSI model, is that the CAN specification strictly covers only the absolute bottom two layers. That's layer 1, the physical layer, and layer 2, the data link layer. These are the foundation, always implemented in pure hardware. All the higher level tasks, those are just layered on top of this in the software.
Now, internationally, these hardware implementations don't just happen by magic. They're dictated by the ISO 1198 family of standards. This family governs basically everything. Part 1 covers the basic data link layer and physical signaling. Part 2 dictates high-speed CAN mediums. Part 3 handles your low-speed, fault-tolerant parameters. And Part 4 is reserved specifically for time-triggered communication. Let's see how this maps to the U.S. market. Here, the Society of Automotive Engineers, or SAE, maintains standards like the J2284 series. Notice how this explicitly specifies high-speed CAN operations at very specific transmission rates, 125, 250, and 500 kilobits per second. You'll also see J2411 on there, which dictates the strict rules for single-wire CAN networks.
All right, Section 3, wiring the D-sub connector.
Okay, we've covered the internal architecture and the abstract standards. Let's move to a practical, real-world example and see exactly how we physically tap into this network. Based on heavy recommendations from the CAN Automation User Group, often just called CIA, the industry standard way to physically interface with CAN controllers and test equipment is via a standard 9-pin D-sub connector. It's that classic D-shaped plug you've probably seen 100 times on testing hardware.
Let's do a quick walkthrough of the actual wiring. If you're wiring up a bus analyzer or an oscilloscope to this connector, you really must methodically map your connections to the standard. Pin 2 is always CAN low. Pin 3 goes directly to ground. Pin 5 is for your cable shield. And Pin 7 connects to CAN high. You absolutely have to get this right, otherwise you won't read any data at all, and you could actually fry some pretty sensitive equipment. So the ultimate takeaway for your physical setup is simply this. The crucial differential voltage signaling, which is the actual communication happening on the bus, happens exclusively across pins 2 and 7. If you're ever probing around for life on a CAN bus, those are the two pins you care about the most.
Next up, Section 4, the controller gotcha.
Before you take all this knowledge, grab a screwdriver and start tearing apart a circuit board looking for these exact chips. Let's look at a major pitfall that constantly trips people up. Because we all learn from generic block diagrams showing three totally separate boxes, people mistakenly assume the CAN controller is always a separate physical chip on the circuit board, usually connected to the microcontroller by an SPI bus. In engineering terms, we call this a standalone CAN controller.
But here's the gotcha. To save precious circuit board real estate and drastically reduce manufacturing costs, the CAN controller is almost entirely integrated directly into the microcontroller in modern systems. It just exists as a peripheral module right on the exact same piece of silicon. So if you're scanning a modern board looking for a standalone translator chip, you're just not going to find it. It's essentially been moved right into the boss's office.
Finally, Section 5, Final Review and Outro.
Let's lock this knowledge in with a rapid-fire review of the most critical engineering takeaways from this explainer. Never forget these three pillars. First, node anatomy. You need a microcontroller, a CAN controller, and a transceiver. That's your boss, your translator, and your megaphone. Second, the OSI map. The strict CAN standard only dictates the physical and data link layers. Everything else is entirely up to your software. And third, the physical connection. On a standard D-sub connector, your actual data lines are always pins 2 and 7. Make sure to hit subscribe to our YouTube channel, Spectrum Speak, for more EMC and automotive communication protocol survival guides. And as you step away from this today, always ask yourself, what unseen, highly coordinated signals are driving the machines around you? Thanks for learning with me today.